Good day, ladies and gentlemen. You're welcome to lecture number 2 of Cmen405, which is Digital Electronics 2. In our lecture number 1, we have seen the basic prerequisites needed by a student taking this course. We also discussed different families of logic gates and how to design them. We look at the design of combinational logic system, and today we are going to continue. And the first thing here is design with universal gates, and these universal gates are NAND gates and NOR gates. The reason why NAND and NOR are called universal gates is the fact that they can be used to implement any logic circuit. And for us to prove that, here are implementation of 3 basic logic gates using NOR and NAND gates. The first thing, if we want to implement an inverter using NAND gates, this is what we do. All we need to do is to use 2 input NAND gates, connect the 2 inputs and deliver a signal which is A. At the output you have A prime, which is exactly the operation of an inverter, not gates. And if we want to implement AND gates using these NOR gates, all we need to do is to use 2 input NAND gates, deliver our 2 inputs A and B through it. We know we are going to have AB all complements, and this is delivered to the input of the next NAND gates, and it will complement it again, that is AB complement. In double negation, we know they will cancel out each other, therefore we have AB at the end of the day. If we want to implement OR gates using these NAND gates, all we need to do is to use 3 NAND gates. As you can see here, we pass A to one of the gates to give us A prime, B to the other one to give us B prime, and these A prime and B prime are now delivered to the third NAND gates. If they enter, we will have A prime, B prime, all prime, and if you use the Morse theorem, it will be the same thing as A double prime plus B double prime, which is equivalent to A plus B. That is OR implementation. And using NOR gates, this is how we do it. For an inverter, we do the same thing. We combine the 2 inputs, or we connect the 2 inputs of a NOR gate together and we connect it to a signal A, and the output should be A prime. For us to obtain OR, all we need to do is to get NOR gates, deliver A and B to it, which will give us A plus B prime as an output. Now if this one enters the next stage of a logic gate, it will be A plus B double prime, which is equivalent to A plus B OR gate. And to implement AND gate using NOR, we use 3 NOR gates. The first one takes in A and produce A prime, the second one takes B and produce B prime, and this A and B prime, they will now be delivered to the input of 2 input NOR gates, and if they go, we will have A prime plus B prime all prime. And if you apply your de Morse theorem, you eventually have A double prime dot B double prime, which is equivalent to A dot B, and implementation. And this is the reason why we call NAND gates and NOR gates universal gate, because they can implement any logic gate you have. Then the next thing is, we can be given a circuit that is made up of different categories of gates. For instance, if you look at this one, we have AND gates and OR gates. We can be asked to convert this circuit into all NAND or into all NOR. And how do we go about that? The next thing we should do, or the first thing we should do, is to understand that whenever you have OR gates but you put double negation at its inputs, it is equivalent to a NAND gate, because this one should be A prime plus B prime if they come out. It's the same thing as this NAND gate, which will take AB all prime, which is equivalent to A prime plus B prime. And also, if you have an AND gate with double negation at the input terminal, is the same thing as NOR gates, as we illustrate here. So using these facts now, we go back to our logic diagram given here. Wherever we see AND gate, we put a cycle on its output, which makes it NAND gate. And if we see OR gate, we put double negation at its input terminal, which is also equivalent to NAND gate as we illustrated. So in this case here, this is my AND gate, I put negation here. This is another AND gate, I put negation here. This one and this, they are all no OR gates, so I put double negation at their inputs, which is equivalent to NAND. And this one is AND gate, I put a negation at its output. This is OR, I put double negation at its inputs, and at the same time I'll put another negation at the output of this OR. The reason why I do this is that this negation and the subsequent ones, they will cancel out, therefore it's like we don't have any negation on the line. Now based on this, we know that this is now equivalent to NAND gate, this one is equivalent to NAND gate. Also this one that has double input is equivalent to double negation at the input is equivalent to NAND. This one is a NAND, and this one has double negation also, it is NAND. The same thing with this. So our equivalent circuit will now be this. But one thing we should take note at is that our input Z here is now connected with a negation at the input of this OR gate, which means whatever you have here, if it was Z, it will now be changed to Z complement, and if it is complement, it will now be real Z now. And we can also be given another example. For instance, we're given this logic diagram and we are asked to change it to all NOR gates. So in the same process, wherever you see OR gate this time around, you put negation at its output, and if you have an AND gate, you put double negation at its input, because we said if you have an AND gate with double negation at the input is equivalent to NOR gate, as you can see here. So I take this original circuit given to me. Wherever I see OR gate, I put negation at the output, AND gate, I put double negation at the inputs. And doing this has changed to NOR gates. This AND gate, it has negation at the output and it has another negation at the other terminal, which means double negation will cancel out. So this AND gate with double negation at the input is equivalent to NOR. This one is equivalent to NOR, and this one is also equivalent to NOR. But at the same time, we can see that here originally in the circuit I have C and D, and here I have B and D. But because of this negation introduced to their lines, I have to change them to C prime, D prime, and B prime respectively. So after doing that, wherever I see an AND gate with double negation at the input, I replace it with NOR gate. Therefore, this is my final circuit diagram with all NOR gates. So the next thing is we are going to see how we can implement Boolean functions using this universal gates, that is using either AND gates or NOR gates. And here is a typical example given to us. We are told that there is a Boolean function f which is equal to a into b prime plus c close bracket plus a prime b, and we are asked to implement it using using NAND gates. That is one of the members of the universal gates. And how we do this is, first of all, we look at what we have inside the brackets and try to implement it. For us to be able to do that, we now say, okay, since in the bracket I have b prime, so I will take real b and deliver it to one of the inputs of this AND gate. And the other thing that is being added to the b prime is real c, so I will now pass it through NAND gate to give me c prime, then pass it to the NAND gate, so that b and c prime are going into this NAND gate as inputs, and this will give me b c prime all prime. If you expand it using the Morse theorem, it will give you b prime plus C, which is exactly what we have in the bracket. Now what is in this bracket is multiplied by A, and for us to get this product, I'll go and take A, combine it with this output, that is B prime plus C, and pass them through an AND gate, and if that happens, it will give me A into bracket B prime plus C, but everything prime because it is NAND gate. The next thing is I should come to this product term, which is A prime B, and for me to get this, I'll go and find A, pass it through NAND gates to give me A prime, take real B, and the two of them pass through this NAND gates, and you see this one will be A prime B, all of them prime. So now I have A into B prime plus C all prime, and I have A prime B all prime. I finally combine the two and deliver them into the final NAND gates as the input, and if they enter, definitely what I should have is A into B prime plus C all prime times A prime B all prime. Now expanding this using the Morse theorem, will come and change this multiplication between the two terms into addition, and this A into B prime plus C that has prime, now it is double prime, which means they cancel out. I have A into B prime plus C, and also this A prime B that has one negation, if I apply my de Morse, it will be double prime, which will cancel out. Therefore this output is equivalent to my F, and if you look at this diagram, we implement it using NAND gates throughout without any other gate. Now the next thing is we move to digital multiplexer. This digital multiplexer is a digital logic circuit that normally takes many inputs but deliver only one of them as output at a particular time. And we know that if we have n inputs, the number of possible output you should have is supposed to be 2 raised to power n, because we are operating in base 2 binary number. So this is the typical block diagram of our multiplexer. If my inputs are from 1, 2 up to 2 raised to power n, then I need selectors that will be determining which of the inputs should be taken to the output at a particular time, and the number of selectors should be equal to that n we have. And here is a typical example, that is 4x1 multiplexer, which means it is a multiplexer that will accept 4 inputs at a time and produce only one of them at the output terminal at a particular time. And for this, we said our inputs are designated by these letters I0, I1, I2, and I3, 4 of them. And if you look at this 4 is equivalent to 2 raised to power 2, which means that power of 2 is my n, which is my number of selectors. And it is generally implemented using AND gates and inverters, and the output of all these AND gates are now passed through an OR gate. Here we have 4 inputs or multiplexer. That is why we have 4 AND gates, 1, 2, 3, and 4. And each of the gates will take only one of the 4 inputs. That is I0 should go to gate 1, I1 gate 2, I2 gate 3, and I3 should go to gate 4. And as we have seen, 2 raised to power 2 we know is 4. That power of 2 is our number of selectors, and we have S0 and S1 as our selectors. In these selectors, we take their real values and we take their inverted values when we pass them through an inverter. So this is our function table. It is the table that will tell us the combination of our selectors that will activate one of the 4 inputs here. Since we have S0 and S1, it means we have up to 4 combinations, 2 raised to power 2, which are equivalent to 00, 01, 10, and finally 11. And as you can see, it is designated in such a way that 00 should be for I0, 01 should be for I1, 10 should be for I2, and 11 should be for I3. So if that's the case, now we know gate 1 to 4 they accept I0 up towards I3. Now, since I know for my I0 I need S0 and S1 to be 0, 0, so I will pass this S1 and S0 to the inverters and their output should be connected to gate 1. For I1 I need 0, 1, which means S1 is 1, S0 is 0, and I will take my S0, which is 0, to gate 2, and the real value of X0, which is 1, to gate 2. Like this, we have all the 4, and this is my corresponding output. It means whenever my S1 and S2 are equivalent to 1, 1, so these inverted values should be 0, 0, and they will go to gate 1 together with my I0. This gate will now be activated and the output is delivered to the our OR gates, which give us the final output. And in reality, this is like internal structure of any multiplexer. It is made of AND gates, inverters, and finally OR gates, that is combining the output of all the AND gates. But in general terms, it is fabricated in form of integrated circuit, and this is the block diagram. These are my inputs, these are my selectors, and this is my output terminal. And within the block, I will write the size of that multiplexer. Like this one is 4x1 multiplexer, and we write MUX as abbreviation of the multiplexer. The next thing is that we can use any multiplexer to implement Boolean function, any Boolean function, depending on what is the number of variables we have in the function. We should select our corresponding multiplexer that will do that work. And we know that a multiplexer can have up to 2 raised to power n inputs, and we set this n stand for the number of selectors we should use for that multiplexer. And as we know, whenever I have a function that has some variables, like I have, this is a Boolean function that has 3 variables a, b, and c, and we know this a, b, and c, if we convert them into the binary form, they will be 2 raised to power 3, which is equivalent to 8. But ideally what we do is, among these 3 variables, we select one of them to serve as our external input, and the remaining should go to our selectors points. And in this case, if we are given a function of a, b, and c, we select any of them. For instance, we can take our a to be the inputs, and b and c should stand for our selectors. And we know, since we have up to 2 selectors, it means my input should be 2 raised to power 2, which is equivalent to 4. So this a must be able to deliver 4 different values. How do we get them? It can be the real a, it can be a complement, it can be 1, and it can be 0. Combination of this can give us the 2 raised to power 2 we know we need at our input terminal. For us to understand this, let us take a typical example. We are given f of a, b, and c, which is equivalent to 0, 2, 3, 5, and 7. We know this 0, 2, 3, 5, and 7, they are our main terms. Now, as we said, among these 3 variables a, b, and c, we take a, in this case, as our external inputs. Then our selectors should be b and c, and b and c means we have only 2 variables. Our n is now equal to 2. Now, for us to find the number of input, we now say 2 raised to power this n, which is 2, will give us 4. It means we are going to use 4x1 multiplexer to implement this Boolean function. And these 4 inputs, they are represented by I0, I1, I2, I3 up to terminated at I3, which will give us 4 of them. And for us to go about doing that, we have to draw what we call our implementation table. And the implementation table is drawn in this way. We have our columns representing the number of inputs we have. Here we know we have 4 inputs, I0 to I3. We put them on this column 1, column 2, column 3, and column 4. Then we have only 2 rows, and these 2 rows will represent our inputs, the real value and the complemented value. I have taken a to be my input, so I will have a prime and a to be on the 2 rows. And we should remember that the first row always take the complemented value, which is a prime. The next one will take the real value, which is a. If you change them, the result will not be correct. And after doing that, we now come and say, okay, the actual function we are given, it is a function of a, b, and c. How many of them? 3, which means if you say 2 raised to power 3, it will give you up to 8. And this 8 start from 0, 1, 2, 3, 4, 5 up to 7, and we arrange them in our table like this. Now we go back to the function given to us. What are the mean terms available? We have 0, we have 2, 3, 5, and we have 7. So these ones we should cycle them in this our implementation table. We cycle 0, 2, 3, 5, and then 7. Now we start with the first column where we have our I0 and check which of the variables is cycled. Is it 0 or 4? Indeed it is 0, and this 0 is on the row of a prime, so I should put a prime to be the input that will be taken to I0. If I come to I1, 5 is cycled and it is under a, then I put a to be the input of my I1. If you come to I2, 2 is cycled and it is on the row of a prime, then I'll take my a prime to be the input to my I2. And finally, if you come here, we have I3 where both the variables 3 and 7 are cycled. So if you have a situation where all the values in that row, column are cycled, you put 1. And in a situation where you have all the values, none of them is cycled, you put 0. In this case we don't have, but that is what we will see in the next example. Now after getting that, we now come and draw our logic diagram of the implementation of that Boolean function. As we have seen, we are going to use 4x1 multiplexer, and these 4 inputs should be I0, I1, I2, and I3, and I have my selectors, which I said I am using B and C, then only one output. Now at the point of I0, I know I need a prime and I connect it here, and at the point of I1 I need a, look at it here, I2 need a prime, then I tap from this I0 and take it to A0, a prime, I take it to I2, and finally I3 needs 1 and I connect 1 to it, and this is the implementation of that given Boolean function. In this case we have only 3 variables, a, b, and c. Now the next example is where we have 4 variables, w, x, y, and z. We have a function f that contains this variable, 4 of them, and we are given the mean terms available in that function. We have 0, 3, 4, 5, 8, 11, 13, and 14. So as we did in the previous case, we take this w to be our external inputs, while the 3, x, y, and z, we take them to be our selectors. So which means my n now is equal to 3. So if I want to find the number of my internal input, I will say 2 raised to power n, 2 raised to power 3, which is what? 8. It means I have 8 different inputs and 1 output. So I'm going to use 8x1 multiplexer to implement this Boolean function. And how I do it is to say this my inputs, they are I0 to I7, and as usual we draw our implementation table. And you know, if you go back to the function, it has 4 variables, w, x, y, and z. 2 raised to power 4 will give me 16, which means I have from 0, 1 up to 7, 8, 9 up to 15 as we have in this table. Now the variable I have taken to serve as my external input is w. You know, the prime should be on the first row and the real w should be on the second row. As usual, interchanging them will make your result to be wrong. Now we go back to the function and see that we have 0, 3, 4, we have 5, 8, 11, 13, and we have 14. Now in order to do this, we now come and cycle the mean terms that are available in the function. We have 0, we have 3, we have 4, 5, 8, 11, 13, and 14. After doing that, I'll come to the first column of I0. here you can see that both of them are cycled. I will have 1. The column of I1, none is cycled, I have 0. Next one, none is cycled, I have 0. Excuse me. And if you come to I3, all of them are cycled, I have 1. If you come to I4, 4 is cycled and it is under W prime, I have W prime here. Here everyone, I have 1. Here I have 14 under W, and here none of them, I have 0. Then after that, I come and draw the diagram. This is my H/1 multiplexer, and my inputs are I0 to I7. Now I0, I know I need 1, take 1 to 8. I1 and I2, they need 0, take 0 to I0, I1 and I2. Then I3 needs 1, I tap from here and deliver it here. I4 needs W, I put W to 8, W prime to 8. I5 1, I6 W, and I7 is 0, and I connect all of them to these 8 different inputs, and my X, Y, and Z go to my selectors S0, S1, and S2. So the next thing is digital decoder. This digital decoder is a digital logic circuit that is used for converting binary information from n inputs up to the maximum of 2 raised to power n outputs. So we always denote it by n to m line decoder, where n is the number of inputs and m is the number of output, and we are told that the output can reach up to 2 raised to power n. Therefore our m is less than or equal to 2 raised to power n. And for example, if we are given a decoder that has 3 inputs, it means the maximum number of output I should have should be 2 raised to power 3, which is equal to 8. This kind of decoder, we call it 3/8 decoder. And how do we go about implementing the decoder? What we do is to draw our truth table that will give us the input variables. Here we set, for example, 3 inputs, 8 outputs. We have A, B, and C as our inputs, and these are the binary values we can have: 000, 001, 010 up to 111. Then our outputs, since they are up to 8, we have D0, D1, D2 up to D7, and you as the designer, you are the one that will select and say, okay, in the first row where I have all zeros, my D0 should be high. In the second one where I have 001, my D1 should be high, up to the last one where I have 111 for A, B, and C, and I say D7 should be high. So if you understand this, we now come and draw the logic diagram. How do we do it? This is the logic diagram. We go to the first one. For instance, if you look at D0 where it is 1, what are the values of A, B, and C? They are all zeros. So I'll put this AND gate to represent my D0. This is the AND gate for D0, and I know A, B, and C, all of them need to be 0. So I'll take A, pass it through inverter, deliver it to this gate. Take B, pass it through inverter, deliver it to this gate, and take C, pass it through inverter, and deliver it to the same gate. So I have 0, 0, 0 for A, B, and C, and that is equivalent to when my D0 is high. And you continue like that until you come to the last one, D7. If you go back, you see that for D7, my A, B, and C, all of them are 1. So I'll take the real value of A, real value of B, and that of C. All of them, I pass them through my AND gate here to give me my D7. This is for 3/8. For any number, we can have 4/16, we can have 5/32. We follow the same procedure. Now, we can also use digital decoder to implement any Boolean function. We know that whenever we are given a decoder, it has up to n input as we have illustrated, and it can produce up to 2 raised to power n outputs. So for this reason, all Boolean functions you can see, you can express them in terms of their min terms, where we have number of variables standing for our n, and the possible output to be 2 raised to power n. And if you want to implement a Boolean function using a decoder, all you need to do is to select the suitable decoder depending on the number of variables you have in the function, and an OR gate which will take all the corresponding output from the decoder and pass them through it and deliver the final output. For us to understand this is a typical example. We have a function f which has w, x, y, and z, and the mean terms available in the function are 1, 3, 7, 8, 10, 13, and 14, and we are asked to use a digital decoder to implement it. In order to do this, we'll now say, okay, these mean terms given to us are 1, 3, 7, 8, 10, 13, and 14, and we know we can express them in terms of those variables w, x, y, and z. For 1, I know I'm supposed to have 0, 0, 0, 1, which means I have w prime, x prime, y prime, and then z, which is the 1. And for 3, I'm supposed to have 0, 0, 1, 1. That is w prime, x prime, then y, z. You continue like this until you go to the last item, and that last item is 14. For you to get 14 in 4 bits binary number, you need 8, you need 2, and you need 4, which means you have 1, 1, 1, and 0. And in this case, you can see that my w should be real 1, x, y, all real, then z prime for the 0 we have. Now, because of the 4 variables I have in this function, w, x, y, and z, I will say 2 raised to power 4 will give me 16, which means I need a decoder of 4 by 16 for input up to 16 possible outputs. And here is the block diagram of my 4 by 16 decoder. These are my inputs w, x, y, z delivered to the input terminal, and at the output, you know, I should have 0, 1, 2 up to 15, which will give me a total of 16 of them. Now I'll go to my function and see I have 1, I have 3, I have 7, 8, 10, 13, and 14. All these ones are tapped from the output of the decoder and passed through the input of OR gates, and finally the output of that OR gate represents my Boolean function. The next thing is digital encoder. This digital encoder is a circuit that performs the reverse or the inverse function of a decoder. This time around, it can take input of 2 raised to power n lines, and it can produce output of only n lines. To implement this, what we'll do, we draw our truth table that will give us the input and the corresponding output. Then we use that truth table to find the expression for each of the outputs, that is the latest representing the output in terms of the input variables. Then we use OR gates to implement the logic diagram. To understand this is a typical example. We are asked to implement octal to binary digital encoder. Octal, we know, is base 8 and binary is base 2. So in order to do this, we say, okay, for octal we have up to 8 possible variables, and we designate them from D0, D1 up to D7, and this octal is 2 raised to power 3. Therefore my n should now be 3, which means my output in binary should be 3 bits, and I represent them by A, B, and C. And as we know, we said the first one, D0 is high, next one D1, next one D2, up to the last one D7, and we have corresponding values for our A, B, and C as the output, starting from 0, 0, 0, 0, 0, 1, 0, 1, 0, up to the last one, which is 1, 1, 1. Now we implement this from the table like this. We look at our table and say, okay, for A, what are the places where I have 1? I have 1 here, I have 1 here, I have 1 here, and here, 4 of them. The first one is corresponding to D4, the second one D5, the next one D6, and the last one corresponding to D7. So I will now take D4, D5, D6, D7, pass them through OR gate, and the output should be my A. Then for B, I have 1 here, 1 here, then 1 here, 1 here. The first one is under D2, the second one is D3. The third one is D6 and the last one is D7. As usual, I take D2 and 3, then D6 and 7, pass them through OR gate to give me my B. I do the same thing for the C. The next thing and the last thing in this second lecture is a digital magnitude comparator. This is a digital logic circuit that is used for comparing two n-bit binary numbers. Supposing you have a binary number A that has 4 bits, maybe you have another binary number B that has 4 bits. Now we use digital magnitude comparator to detect whether A is greater than B, or A is less than B, or A and B are the same. So to understand this, we first of all express our two binary numbers. Here is A, which is A3, A2, A1 and A0 as the 4 bits inputs, and my B has B3, B2, B1 and B0 as my 4 bits. The next thing I will do is now to start the comparison, and I will do the comparison with respect to the level of significance. I will compare A3 with B3, then compare A2 with B2, then A1 with B1, lastly A0 with B0. And whenever you have a excuse me, if you have a particular A, let's say AI is 1, but the corresponding B, that is BI, is 0, we know that A is greater than B. But if AI is found to be 0 and BI is found to be 1, then B is greater than A. But in a situation where you found that AI and BI are all equal to 1 or all equal to 0, which means you cannot decide at that point, you have to go to the next level of significance until you find the difference, if any. And if you want to do this one using a discrete logic diagram, you need, if you have n bits number that you want to compare, we need up to 2 raised to power 2 raised to power 2n in your truth table. For instance, this ones we have 4 bits. It means our truth table should have 2 raised to power 2n, that is 2 times 4, 8. 2 raised to power 8 is a very, very big number. So in order to avoid this, the magnitude comparators are normally fabricated in form of integrated circuit. A typical example is this IC, which is 74HC85. It is 4 bits magnitude comparator, and this is the typical block diagram. It is DIL, that is dual inline package. You can see that this is our pin 1. As we know, we calculate determine the number of pins by going in anti-clockwise direction. So this is my pin 1, pin 2 up to 7, then 8 up to 14 on the other hand. And as you can see on the diagram, my B3 is on pin 1, then pin 2, 3 and 4, we are using them for cascading. What do we mean by this cascading? For instance, if I want to compare two 4 bits binary numbers, this IC is enough to do that. But if I want to compare 8 bits, all I need to do is to take one of this IC and connect it with the corresponding IC, so that this one will take 4 bits and the other one will take 4 bits, so that I can now compare up to 8 bits. In a situation where I want to compare up to 12, I use 3 ICs. This pin goes to the next one, and this one goes to the last one, in this way. And here are our outputs. This output is high when A is greater than B. This one is high when A is equal to B, and this one is high when A is less than B. Pin 7 is my ground, and this is pin 8 for B0, pin 9 for A0 up to pin 13 for A3, and my VCC, that is the supply, is at pin 14. And for us to see how this IC operates, we have our table of comparison, and as we said, we take each significance level and compare them. So the first level here is A3 compared to B3, A2 compared to B2, the next one A1, B1, the last one A0, B0. And how do we go about doing this? We first of all compare A3 and B3. If we establish that A3 is greater than B3, so I don't need to compare A2, B2, I don't need to compare A1, B1, also A0, B0, no need. So that's why I put X, these are don't care conditions. I can conclude that my A is greater than B. This is why I have high here in the other terminals low. But if I establish that A3 is less than B3, still I don't need to find 2, 1 and not. I just say that my A is less than B, that is why I have high here, the others low. But in a situation where I found that A3 is exactly equal to B3, I have to go to the next level, that is compare A2 and B2. And if I found that A2 is greater than B2, so I don't need 1, 1 and not, I can say A is greater than B. But if I found that A2 is less than B2, still I don't need to compare A1 and B1, A0 and B0. I just say my A is greater than B. This is high, the others are low. Also, if I found that A2 is equivalent to B2 while A3 and B3 are the same, then I have to go to the level of A1 and B1. If A1 is greater than B1, then this is high, the others I don't need to know them. But if A1 is less than B1, I can say my A less than B is high and the remaining no need. But at the third level, if you found that A1 is equivalent to B1 while A3 equivalent to B3, then A2 B2, then you have to go to the last level, which is A0 compared to B0. If A0 is greater, this is high. If B0 is greater, this is high. But if still A0 and B0 are the same, it means A and B are equal. Here I have high, the remaining are low. So gentlemen, this is the end of today's lecture. I would like to advise you to watch it over and over again. In case you still have problem, you can contact me personally to discuss about it. Thank you very much till we meet in our lecture number 3. Thank you.